All right, this is lesson 3, electric fields. So we've just completed lessons on electrostatics and Coulombs law, and now we're going to study an electric field. An electric field is a force field. It's a type of a field, not a force field, but it's a field like a gravitational field that can produce force. So here's a question that exhibits that. The figure shows a positive charge placed in a uniform electric field. Is the force exerted on the +1 Coulomb charge, positive charge, directed up or down? So the principle here is that electric fields go from positive to negative. So up here on the top would be a positive plate, if you want to think of it as that, and down here is a negative plate. So that's the direction of electric field. So if this is a positive charge, it's going to be pushed away from positive and down towards the negative. So the answer to that would be downward. All right, a positive charge will move in the direction of an electric field, positive to negative, so the charge above moves downward. The formula for electric force is force electric, Fe, equals QE. So electric force is Fe, Q is charge, and E is electric field. Compare this to the gravitational force. W, which is weight. Now your weight, what you refer to as your weight, is a force. It's a force on the earth caused by a gravitational field. So W, weight, equals mass times gravitational acceleration. So what that means is, the way you parallel these is they're both forces. Weight and electrical force are both a force. An electric field works on an electric charge. A gravitational field works on an object's mass. So the more mass a person has, the more weight they will have. The stronger the gravitational field, for example, the gravitational field on Jupiter, a bigger planet than the Earth, would have a stronger, the person would have a greater weight. So now a mass will not move in an electric field. For an electric field to have an effect on an object, it has to have an electrical charge. But a gravitational field will have an effect on any object that has mass. So both Fe and W are forces. Mass M is the object the gravitational field acts on. Charge Q is the object the electric field moves on. The interaction of the field with the object creates the force. All right, on square 4, as we move down, electric field can be expressed as electric field equals force over Q. That's just simply taking that and rearranging it. This is they took Coulomb's law. This is really not important for you to know how to derive this. I'm just going to show you how did they get this. It's Q1 Q2 over D squared. That's equal to force by Coulomb's law. So if you take electric field equals force, Fe, that's all of this, and put it over Q. So you put a Q down here. Then one of these Q's is going to cancel, and so you have KQ over D squared, and that's where that comes from. That's not important to know, but just have this on your formula sheet. Okay, so square 5 asks you a question. A point charge is, think of it just as an electron or a proton. It's really a theoretical imaginary charge that doesn't have an influence on the electric field. So they want to say, if there were a charge there, how would the electric field act on it? But you can think of it as a proton or an electron. So a point charge is placed 3 meters from a 4 microcoulomb charge. So remember, that's 4 times 10 to the -6. That's what a micro means. What is the strength of the electric field on the point charge at this distance? All right, so down here, you have electric field. You have a distance they gave you, 3 meters. You have the Q, which is 4 times 10 to the -6th. And you have Coulomb's constant as well. So they're simply going to plug that into this equation right here. And so we go to the next page. And there's the formula. So there's K right there. There's Q right there. They just have one charge. And there's the distance squared. So it's 3 meters squared. So again, the way you do this is 3 meters squared. First of all, just go ahead and square that. That's 9. So 8.99 times 4 divided by 3. And then, so that's what you do right there. Divided by 3 squared, rather. So that's what you do right there. And all of that gives you 3.99, and then you take care of the exponents. Not this one, because it's not scientific notation. We've already dealt with that number. That was 9. But these two. So 9 minus 6 is positive 3. So the answer is 3.99 times 10 to the third. Again, they like you to convert things into a non-scientific notation number. So what you do is you come over here, 3.99, you write the coefficient. This is in the scientific notation video. And it says you're going to move this 3 places. Which way? Well, 10 to the third is a big number. It's 1,000. So it's bigger than this. So to make this a bigger number, you move it to the right. So it's 1, 2, 3. It's right there. You put a 0 right there. And what you get is 3,990, and they just rounded that due to significant figures to 4,000. Don't worry about significant figures. If you wrote 3990, that's good enough. All right, let's keep moving. Another problem here. So this is square 6 in the instruction part of the electric fields lesson. So at the position of a proton, the electric field generated by an electron orbiting the nucleus of a hydrogen atom is 5 times 10 to the 11th newtons per coulomb. So that's an electric field. So there it is right there. They've written that out for you. And you want to do that is write out your variables like that. Because a lot of times what will happen is when you do that, you see an E and a Q, and you know there's a K in there, coulombs. The formula jumps out at you. You don't look for the formula first. You look for what variables you have and what you're trying to find first. Okay, so what is the given radius? Okay, so they're going to again use this formula up here. I'll pull it down a little. Well, there's the formula right there. They're going to use that formula right there. So they're giving you E, K, and Q, and they're asking you to find D. So maybe the hardest part for some of you would be the algebra on this, so let's work on that. So if you just plug in the numbers, you end up with, there's the electric field right there, there's Coulomb's constant right there, and there's the there's the charge right there. And what you don't know is D squared. So what you got to do is get D by itself. That's how you solve for D. So the first thing you do is you multiply both sides, top and bottom, by D squared. So I'm going to come over here way off to the side and put that in parentheses. And what that does is D squared here cancels with D squared there. Then you also have to write D squared over here, and I'm going to do that on the next line down. The next thing you have to do is you got to get D by itself. So you got to get rid of this thing. The way you do that is you divide both sides by 5 times 10 to the 11th. So that's what these arrows are indicating, that the D squared is going to come up here and that this term is going to come down here on the bottom because you're dividing both sides by it. So what you end up with there is you end up with D squared equals Coulomb's constant, there's the charge, and there's this electric field that was on the other side. What do you do about this D squared? Well, the way you get that D out of D squared, the way you undo a square is by taking the square root. That's an inverse operation. So you come down here, you take the square root of D squared, and that gives you D. That's what you want. That's what you're trying to find. But if you take the square root of the left side, you have to take the square root of everything on the right side. So what you do is just do the math on all of this stuff inside of here. And then once you're done with that, then take the square root of that number. So it's 8.99 times 1.602 divided by 5. And then the exponents are going to be 9 minus 19. That's going to get you to negative 10. And then an exponent on the bottom is subtracted. So negative 10 minus 11 is negative 21. So let me write out what you're going to get before you get to this final answer. And I'm going to show you how to do it on the calculator. Okay, so here's what I'm going to do. I'm going to take 8.99. I'm going to multiply that by 1.602. And I'm going to divide that by 5. And that gives me 2.88. That's far enough. We don't have to deal with all those other digits there. 2.88. So I'm going to write that down. And I'm writing it right here. Now I've got to deal with the exponents. Now be careful on this. You add the ones on the top and you subtract the ones on the bottom. So it's going to be 9 minus 19. That's going to get you to negative 10. Then you have to take negative 10 minus 11 because 11 is on the bottom. That's, again, watch the scientific notation video. So negative 10 minus 11 is negative 21. So it's 2.88 times 10. to the negative 21 power. It's a pretty small number. But that you got to then take the square root of that. So I'm going to show you how to do this. I'm going to show you just a little calculator technique. Well, I don't need to in this case. I'm going to just go ahead and do it. So what I'm going to do is second and x squared. That gets me a square root plus an opening parenthesis. You have to remember to close that at the end. And let me show you how to put in a scientific notation number in a calculator. It's 2.88 times 10. And this little hat here that's called a caret or a hat or looks like a roof of a house, you hit that and that makes an exponent. So it's that, and the minus sign is not this sign. That's a subtraction. You want to hit this one down here at the bottom. That's a negative sign. So you hit this one, not that one for a negative sign. So it's to the negative 21. And now remember what I said, you have to close that parenthesis because you had an open parenthesis. So now what I'm doing is taking the square root of this number because that's what the equation says to do. And I get 5.36, and they round that to 5.4 times 10. And there you see the exponent up there in the corner there, negative 11. So it's 10 to the negative 11. So there's your answer right there. In part of this class, a little bit of it is getting used to handling a calculator. Some of you have different calculators. Some of you have cell phones, but your cell phone all have a square root function on it. All right, let's keep going. So down here, an electric field of 3 times 10 to the 16th Newton per Coulomb is needed to create a spark in the air. If the charged particles in the field are separated by a distance of 1 millimeter, how many coulombs of charge are needed for the spark? So first thing you got to know is a millimeter is 1/1000th of a meter. And generally, when you're working in these units, you've got to be working in meters, not millimeters. So that's kind of a trick that, and again, it's one of those things they assume you know how to do that you may not know how to do. So how do we do that? So it says 1 millimeter. And I'm going to show you how to do a conversion here. And there's 1 meter for every 1,000 millimeters. If you look at a meter stick in your classroom, when you were in your classroom, you would see all these tiny little lines that were just a blur. They were so small you could barely see them. Those are millimeters along a meter stick. Okay, so what you do is you cancel the units. Millimeters and millimeters cancel, top and bottom, and you're left only with meters for your final answer. So you go to your calculator and you divide 1 by 1,000, and what you get is 0.001 meters. That's how much 1 millimeter is. Again, this 0 really doesn't mean anything. It's just put there by tradition, by convention. But these do. Okay. All right. So anyway, there's Q, there's E, and there's distance. So let's go to the next page. Okay. And again, the formula that we're using is E equals K, Q. That's my way of making Q. So get used to it. Over D squared. I never learned a good way to make a Q, so that's the best I can do. All right, so here it is. There's Coulomb's constant K. There's the charge is what you're looking for, so you're going to have to do a little algebra here. And there's the distance down there squared, 1 meter, 1.001 meters squared. And over here is the electric field. So that's the electric field. So we're trying to find this. Okay, so again, with a lot of these problems, the hardest thing is the math. Once you got the equation set up, because you're dealing with scientific notation, you just got to get used to it. So I have the electric field, Coulomb's constant, and the charge over the distance squared. So what you do is you have to isolate Q. You're solving for Q. You're trying to find that. So what that means we need to do is divide both sides by this. That'll make this disappear. And multiply both sides by this. That'll make this disappear. And the Q will be there. So if I do that, I divide both sides by this. There it is right there. It's on the bottom now on the other side from Q. And I multiply both sides by this on the top. So there it is on the top on the other side from Q. So now Q is all by itself. So now you're going to multiply 3 times 0.001 divided by 8.99. And we'll go ahead and do that on the calculator. Just show you how you would work that on a calculator. So it's 3 times 0.001 squared, I should have said. And then you're going to divide that by 8.99. So 3 times 0.001 squared divided by 8.99, and that gives you this really tiny number. So I'm going to write that. It's 0.0000. That's how many zeros? 1, 2, 3, 4, 5, 6 zeros in front. So that 0 doesn't count. So 1, 2, 3, 4, 5, 6, 3, 3, 4. Okay, so now we've multiplied 3 times this to get that number. Now we've got to take 10 to the 16th minus 10 to the 9th. So it's 16 minus 9, and that's going to equal times 10 to the 7th. Again, when you have exponent top and bottom, a division, it becomes a subtraction problem. So 10 to the 7th. So now we finally want to get our final answer, 10 to the 7th. So this means we're going to make this number bigger. So to make it bigger, because it's a positive number, we need to move the decimal to the right. So it's 1, 2, 3, 4, 5, 6, 7. It goes in between the two 3's. And there's your final answer. Q equals 3.34 coulombs. Okay? So again, the messiest part of that is just the math, and you just got to get used to dealing with the math. Okay, square 9. Electric field lines travel from positive point to a negative point. Okay, we've been over that point quite a few times in a curved fashion. So it's like throwing a ball. Again, it's forces, so it deals much like gravitational force. If you throw an electric field up this way, it's going to curve around like a ball thrown in the air and come back down right there. Electric fields that change direction are called non-uniform electric fields. So it's just a term to know for the test. So something they might ask you. So anything that you see the lines curving is called non-uniform. Electric fields lines that travel in straight line have equal strength create a uniform electric field. So straight lines like that are a uniform electric field. All right, and finally, square 10. It's just a problem that they gave you. So based on the image, the charge of the red circle is, well, remember electric fields go from positive to negative. So the blue one's going to be a positive. You can put a little plus sign there. And this one's going to be a negative because the field lines are going towards it. So that's going to be negative. The charge of the blue circle is positive. The strength of the electric field between the two charges is strong compared to the field outside the charges. In other words, where the lines are closest together is where the field is the strongest. So you can see they're closer together in between than they are out here where they're more spread out on each side there. Okay, and the force between the two charges is attractive. So if the lines go from one to the other, that's an attraction. If they push away from each other, like you've seen in earlier part of the lessons, then and they don't connect, then that would be repelling. Okay, that takes care of electric fields, and we'll move on to Ohm's law in the next video.